Good morning, everyone. Welcome to the December Pacific Northwest DEWS Drought and Climate webinar. My name is Erica Fleischman, and I'm with the Oregon Climate Change Research Institute and Oregon State University. We are one of the hosts of this bi-monthly webinar series, along with NIDIS and the USDA Northwest Climate Hub. The webinar is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar is tailored to reflect recent, current, and forecasted conditions and climatic events, and also to include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week, and if you're signed up for our emails, you'll receive notifications when those are available. Today we have 4 speakers lined up. Zach Hoylman, who I believe submitted a remote presentation due to a last-minute conflict, will discuss a climate recap and current conditions. Then we'll switch to seasonal conditions with Andrea Baer. Larry O'Neill will discuss how El Niño and La Niña affect reservoir storage across the Pacific Northwest region. And Jessica Lundquist will discuss seasonal peak snow predictability. We'll use the question and answer box on the right side of your screen to collect questions during the presentation, and we'll do our best to address those and any additional questions during the question and answer period after the 4 presentations. Before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops science-based, region-specific information to assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. And I will post links to each of these organizations in the chat box. The Oregon Climate Change Research Institute is a network of researchers at Oregon's public universities who work with the public and with private entities to advance understanding of regional climate and climate adaptation. OCRI is administered by Oregon State University and hosts the Oregon Climate Service, which is the Office of the State Climatologist of Oregon. The 7th Oregon Climate Assessment will be released on January 7th. The National Integrated Drought Information System was established in 2006 by public law with a mission of improving the nation's capacity to proactively manage drought-related risks by providing those affected with the best information available and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that can help communities cope with drought. Although the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the regions. Each DEWS has many of the same basic ingredients, but ultimately has their own flavor to reflect the needs of their region. The Pacific Northwest DEWS was launched in February 2016, and our strategic plan and information on current activities is available at drought.gov. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCORAS, the Community Collaborative Rain, Hail, and Snow Network. This is a distinct, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation in the form of rain, hail, and snow, and to report conditions. Observations by COCORAS observers of precipitation events and even the lack of precipitation are important to capture and improve understanding of weather. To become a volunteer or to learn more, visit cocoras.org or contact your state coordinator. Understanding how drought impacts you is important for drought assessment at the state, regional, and national levels. The National Drought Mitigation Center's Condition Monitoring Observer Reports, or CMOR system, is a great way to submit information on the impacts you're experiencing, whether the cause is too little water or too much water. If you become a regular observer, your information will be available to those who assess drought in your state And we also pull from this information for the annual Pacific Northwest Water Year Impacts Assessment. I will drop a link in the chat of a location where you can go to watch a how-to video, learn best practices, and access various forms of information. Snow drought status updates. These have begun. For this year, they were launched in 2018. The updates provide timely information on snow conditions across the West with an emphasis on snow drought. The most recent update was attached less than a week ago on December 11th, and the next update will be released on January 8th. And you can find the most recent information here. Notices also will go out on social media when those are released. There are new ways to stay in touch with NIDIS. If you registered for our webinar in the past, we were able to add you to the Pacific Northwest DEWS email list so that you would receive the recording. This is no longer the case, so if you received notice of this webinar in any way other than a direct email and you'd like to receive DEWS information, please follow the link that I'll place in the chat box to sign up. We have a bi-weekly Dry Times newsletter and a tribal engagement newsletter. And here is the link to sign up. All right, transitioning now to today's kind and excellent speakers. The first speaker is Zach Heilman. We will provide all speaker contact information and presentations after the webinar. And please mark your calendars for the next webinar in late February.
Erica, please make sure that you can see the screen here, and that also when I do start it, that it is audible. Thanks.
Yes, can see the screen. So we'll get into Zach Heilman's presentation now.
I'm a state climatologist in Montana. I'm excited to be here to kick off the climate and current conditions recap for the Pacific Northwest. Drought has been a persistent feature of this landscape this season. And while it's been unseasonably warm and dry the last several months, there have been some improvement to those drought conditions across the region. Despite these subtle improvements, there remain some important drought impacts, especially related to stream flow in the headwaters of the Columbia Basin. And with that, I'll go ahead and get started. My presentation today will focus on how the conditions we've experienced in the last couple of months compare to historical conditions. And specifically, I'll focus on the last 90 days of precipitation and temperature, the last 30 days of precipitation and temperature, current early season snowpack conditions, soil moisture, stream flow, and the resulting drought conditions. I'm going to attempt to complete all of this in the next 10 minutes and then hand it off to the next speaker for a discussion of our seasonal outlook. All right, so let's start with what we've experienced in the last couple of months, specifically the last 90 days. In this slide on the left, I've shown the temperature departure from normal for the last 90 days compared to the 1991 to 2020 climate normal. Blue shading represents cooler than normal conditions, while red shading indicates warmer than normal temperatures. Overall, you can see that essentially the entire region has experienced either much warmer than normal temperatures or near normal temperatures. There's very, very little blue on this map. These deviations from normal range from about 0 to 5 degrees Fahrenheit above normal on average. That's a considerable deviation over such a long period. Notably, statewide, Montana has the second warmest 3 months on record over the last 130 years. The figure on the right shows our anomalies in precipitation over the last 90 days. Increasingly brown areas represent below normal precipitation, white areas represent normal precipitation, and green areas represent above normal precipitation. I'll call your attention to the area of brown from north central Idaho extending northward into western Montana. Here, precipitation has been well below normal, with only 50 to 90% of normal for the last 90 days for the majority of this region. On the other hand, portions of eastern Oregon have experienced slightly wetter to much wetter than normal conditions, with values ranging from about 110 to 200% of normal precipitation. As we transition to the last 30 days, we see similar temperature patterns across the domain, but with some more variability. Starting with temperatures on the left, And using the same color scaling as before, you can see that Idaho and western Montana are much warmer than normal, continuing the pattern from the 90-day anomalies we saw on the previous slide. Western Montana is the major hotspot of this anomaly, which has contributed to some pretty important impacts to stream flow. We will evaluate these impacts later on in a future slide. However, the coast of Oregon has generally had cooler than normal conditions. Overall, you can see that there are localized pockets of hotter or cooler than normal conditions across the Pacific Northwest, with some consistent patterns to the 90-day anomalies in the eastern portions of the region. Shifting to the right once again following the same color scale as the previous slide, precipitation deficits over the last 30 days show drier than normal conditions across Montana and Idaho. Notably, large portions of southern Idaho only receive 5 to 25% of normal precipitation, which is indicated by that dark brown color. Most of the coastal regions in Oregon and Washington are drier than normal over the last 30 days, but the anomalies are generally less severe than those in Montana. However, there are also stream flow impacts in this region that we will explore in a future slide. Also important to note is that it has been slightly wetter than normal over the last 30 days in central Washington and eastern Oregon as well. Okay, so how have these variable conditions impacted the early part of the snow accumulation season? Well, on the left, I'm showing the percent of average snow water equivalent, or SWE, for December 14th across the mountainous regions of the Pacific Northwest. These data are measured using snow pillows at snow-tell sites across the Rocky Mountains and the Cascades. You can think of snow water equivalent as the amount of water that would exist as a depth if we were to melt the entire snowpack at a point. On the right, I'm showing a slightly different estimate of SWE anomalies calculated using a snow model maintained by NOAA called SNODAS. Let's start by looking at the snow-tell data. The left-hand figure shows the average snow water equivalent for each watershed. Yellow and orange shading indicates below normal snowpack conditions, green indicates normal conditions, and blue indicates above normal conditions. As you can see, the snow accumulation season has generally been above normal in southwestern portions of the region, on track for what we would expect for this time of year in the central portions of the region, and well below normal in the eastern portions of the region. So far, the main area of concern in terms of snow accumulation, according to SNOTEL, is in Montana and Idaho. However, it is important to note that it is still quite early in the snow accumulation season. There's much time for these conditions to change. Let's shift to the right-hand figure now and look at the SNODAS dataset. The SNODAS model takes an assimilation approach to estimating snowpack dynamics, leveraging both a snowpack model as well as observations such as SNOTEL data to make estimates. The main difference here compared to SNOTEL is that SNODAS estimates snowpack across the entire basin, low to high elevations. Here we can see a generally similar story to SNOTEL, where snowpack is generally following the west to east pattern with more snow in the west. However, this model is indicating that some mid to low elevation snowpacks are off to a slower start in portions of Washington. Spatially distributed models like these are useful for understanding how the snowpack is distributed across watersheds and giving a more holistic picture of snow accumulation. The persistent but variable drought conditions continuing from the last few years, in conjunction with the lack of significantly above precipitation, Short-Term Prediction Research and Transition Center, also known as SPORT, modeled soil moisture product in percentiles for December 13th. Red colors represent below average conditions, while blue colors represent above average conditions. As you can see, soil moisture is generally below average in the eastern and central portions of the domain, following precipitation anomalies, especially in southern Idaho. There are some locations with wetter than average soil moisture conditions in Oregon and Washington as well, but they are generally spatially discontinuous. In general, soil moisture is quite variable, but dry antecedent conditions now, like those in Idaho and Montana, can be cause for concern for the next season as the soils thaw. Looking directly at current stream flow conditions now, here's a map of USGS stream gauges and flow rankings across the Pacific Northwest over the last 28 days. Across the gauge network, blue symbols indicate greater than 90 percentile flows for this time period or well above average stream flow. Light blue is between the 75th and 90th percents. Green is between the 25th and 75th percentiles or near average. Orange is in the lowest 10% to 25% of flow, and red is in the lowest 10th percentile or well below average. Generally, the majority of gauges across the region are indicating normal flows, besides portions of Montana, Idaho, and Washington. In Montana, the persistent drought conditions and lack of precipitation have contributed to extremely low flows in the major river basins, such as the Blackfoot, Clark Fork, and Bitterroot basins. These are important headwaters of the Columbia. I'm also showing the Blackfoot River on the bottom right, where flows have been at or near record low almost all year. Recent anomalies in precipitation have also led to low flows in parts of Washington. On the top right, I'm showing one of these basins near Seattle where flows are also very low, but more recently. Summing all these observations up, let's take a look at last week's United States Drought Monitor map, updated by Curtis Rigonanti. As you can see, drought continues to be persistent across the eastern portions of the Pacific Northwest, despite some improvements. However, the western portion of the domain is showing much less drought. Low stream flow, dry soils, and precipitation deficits over the last 3 to 24 months and even longer have produced regions of severe or D2 and extreme or D3 drought conditions in Montana and Idaho. However, the remainder of the region has had much improvement in the last several weeks, resulting in no drought across much of Oregon and Washington, according to the U.S. Drought Monitor. Let's take a look at some of the recent changes. On the left, I'm showing you a 3-month change map of U.S. Drought Monitor classes, and on the right, a 1-month change map. Green shows areas of improvement, while yellows and browns show areas of degradation. Starting on the left, you can see that drought has generally improved across Oregon, Washington, and northern Idaho and northern Montana. This is similar when looking at more recent 1-month improvements as well. And to summarize my presentation, temperature has been much hotter than normal over the last 30 to 90 days across the majority of Montana and Idaho, with more normal and moderated conditions across much of Oregon and Washington. However, the last 30 days have been much more spatially variable, with some hot and cold spots in Oregon. However, Montana and Idaho still remain very hot regardless of the time scale, 30 or 90 days. Precipitation over the last 30 to 90 days have generally been drier than normal in Idaho and Montana, as well as portions of western Oregon and Washington. And these meteorological conditions have resulted in variable soil moisture conditions, reduced stream flow, especially in portions of Montana and in Washington, for example, some of the tributaries near Seattle. And snowpack is showing encouraging accumulation so far in the west and a slower start in the east. However, it's very important to note that we have a long way to go before the snowmelt season actually occurs, and so these conditions could change dramatically. And with that, I'd like to say thank you and pass it off to the next speaker.
Great, thank you, Zach. Obviously, since Zach is not here with us in person, it's a little bit difficult to ask him questions directly, but if you have questions, feel free to email them to us and we will convey them to Zach and hopefully be able to get back to you with an answer. Our next speaker is Andrea Baer. And Andrea, I'll give you a heads up around 12 minutes.
Okay, great. I only put 12 slides in here, so hopefully I'm good. Good morning, everyone. Again, my name is Andrea Baer. I'm with the National Weather Service. I'm actually located at the Western Region Headquarters office, which is located in Salt Lake City, Utah. And I'm the Climate Services Program Manager for the Western Region. I'm going to start out today talking a little bit about La Niña and where we're at with it. It's an interesting case this year. It hasn't developed like we typically see. But then more and more, I think the El Nino and La Nina patterns are leaving us guessing sometimes. They don't quite develop exactly like we expect. So under typical winter La Nina pattern, the jet stream is shifted further to the north, and the Pacific Northwest tends to benefit with wetter conditions and cooler conditions, which spread into the north central portion of the US. And I won't cover the rest of it because we're only concerned with Pacific Northwest today. So hold on, my computer. Whoops. All right, here we go. Now it's moving. All right, so the National Weather Service still has a La Nina watch in effect. The potential for La Nina has been very slow to develop. We keep saying this, and it keeps going another month. It's been very slow to develop. It is far into the calendar year, and we're getting into 2025 soon. So we don't expect it to be any more than a week event. If it develops, it will probably just touch those thresholds for La Nina for a few months, but it may not even be considered a full-fledged event when we get through with the winter and move into the spring, simply because it's so late in forming. La Nina, it is, like I said, still favored to emerge sometime in this next season that we're currently in, so November, December, January, about a 59% chance of that, and transitioning to ENSO neutral in the March, April, May season as we get into spring. The sea surface temperatures have really only been slightly cooler than average. I'm going to show you what it takes, kind of a recipe for La Nina in the next slide, but overall it's the sea surface temperatures that are really holding this up. The atmosphere is exhibiting more typical La Nina behavior, what you would expect in the atmosphere in the tropical Pacific. But yeah, it just hasn't coupled so well with those sea surface temperatures. They haven't kicked in quite yet. I just want to remind folks that the stronger a La Nina event is, that means it's more likely to get more typical impacts. So the wetter, the cooler that I showed in the previous slide, that's the stronger an event is, the more confidence we have that we will see a lot of those typical type of impacts. This again is forecast to be a weak one, so a little bit of uncertainty increase in this situation. So in the graphic I have here on the left, I just want to show you how this event has evolved. And this is looking along the equator, just a little bit north of the equator and south of the equator, but that entire region. And I'm hoping my cursor is showing up on the screen there, but as you can see, we moved out of that big El Nino event that we had last year and started cooling things off in the spring. And as we've moved through the spring into summer and now into fall, and as we're getting into winter, we have seen mostly near to below average sea surface temperatures along that eastern Pacific. They expanded west and have done that. Not very strong anomalies, but nonetheless cool anomalies. So what do we typically look for to determine whether we're in La Nina conditions? Well, the sea surface temperatures in the tropical Pacific Ocean need to be cooler than the long-term average by at least about -0.5 degrees C. For the atmosphere, and all of these atmospheric components are currently going on right now, but we tend to see stronger trade winds, or those easterly winds along the equatorial region, more rain over Indonesia and less rain over the central Pacific. I just want you to note in this is a really nice graphic that I took from the ENSO blog on climate.gov. And overall, you can really see the warmth of the oceans globally, with the exception of the few patches of cool, including our ENSO watching area there that is marked with the box around it. But you can see how warm the oceans have been, and it's been this way for well over a year now. And, you know, likely that's having an influence. Exactly how much of an influence is something researchers are looking into, but it's definitely having an influence and probably the reason we are so slow to develop this La Nina this year. So looking at some of the current conditions right now, in the center graphic in that Niño 3.4 region, I want you to notice as we moved from August all the way to December, and we're halfway through the month now, we have been on the cooler side. We've been hovering around that sweet spot of the minus 0.5 degrees Celsius. So we've been hovering along that for a little while now. And as you can see in these weekly departures, to the left there, that sweet spot that we look for, which is right in here in the Pacific Ocean, is reaching that threshold. But keep in mind that's only a weekly departure from normal. So we go with monthly departures from normal, but we are looking like we are in that La Nina territory. So we'll see what happens by the end of the month. I do want to point out that we've got plenty of cool in the sub about 300 meters down along the surface of the ocean, or excuse me, down in the upper ocean, down to about 300 meters. And things have been on the cool side starting back in February and moving all the way into December, and we're currently in a dip for the subsurface to be a little bit cooler. So all indications moving towards La Nina. So looking into the forecasts a little bit, if you look at the official forecast that comes out of our Climate Prediction Center, you can see the blue indicates the % chance of La Nina to develop. So currently in that November, December, January season, and around 59%. As we move further into the winter though, the odds increase a bit, a little over 70%, and then back down, and then looking to go into more neutral territory as we get out of the spring and move into the summer. On my right is the International Research Institute's ENSO forecast plume. This shows all of the dynamical models and the statistical models that go into indicating what phase we're in of ENSO. And I want to point out, you're going to hear me say this quite a bit in the next few slides because of the timing of the month. A lot of my graphics are stale, so I have put links here so you can go look at them. Everything's coming out this week, but our briefing is on Monday, and so I'm at a disadvantage here. But this is the model predictions from November, and looking at the average of all of these dynamical models, which are listed right there at the top. Hovering right below, right along that threshold of a weak La Nina. And the statistical model is a little warmer, showing we're pretty solid into a more of a cool, neutral situation. So again, in the next 2 days, that should be updated. We should have new December forecasts. So looking at the climate forecast system, one of the forecast models that our Climate Prediction Center uses, which is the CFS, version 2, the ensemble mean, which is this black dashed line right here. Basically what this is showing us is that conditions should develop soon and persist not very long. So February, March, April. So really not expecting a very long cool event here with La Nina. Talking a little bit about impacts, I mentioned the wetter, the cooler, typical impacts we get in the wintertime, but I want to talk a little bit about snowfall. I took this also from the climate.gov's ENSO blog, so you can go read this article for yourself. I've put the link there if you want to dive into this a little deeper than what I have time for here. But what I want you to notice here, this is taking all 22 on the left here, all 22 La Nina winters that we've had back to 1950s. And what you're seeing here is you can definitely see the snowfall being above average in the Pacific Northwest area, especially those mountain ranges, of course, and up into Canada. And it's kind of hard to say, to put everything into perspective by saying, okay, we're going to average 22 winters, because if you had one big or a few really big snow dump years where you've just got a ton of snow, very well above average, that's kind of going to skew what the actual message is. So what they did is they took out and looked at just the weak La Nina winters. So looking at just La Nina weak winters, which is what we've got a situation of this year, you can see just things are a bit more muted, but still we've got a pretty good chances for above average precipitation. Though I will say there are some areas that show up during weak winters and have not produced those nice epic snowfalls above average. Looking on the border there with Canada, and then up further into coastal Canada there, and then also straddling the central Oregon and Washington line there. So again, impacts tend to be more muted during weak events, and this is a nice indication of that. All right, so now I have to caveat again, all of my forecasts and outlooks that I'm going to show you, all of them are outdated. They'll all be updated. And first of all, these right here, the 8 to 14 day outlooks, the temperature and precipitation, I am showing you those. Those were done by our computer models yesterday, but our forecasters will be updating those right after this call. So head on over to the CPC website, and you can see the latest with our forecasters input in there today. But basically expecting a warmer and wetter regime for the Pacific Northwest as we move into the Christmas holiday.
Andrea, we'll need to be wrapping up, please.
Okay, gotta hurry. Okay, thank you. These are the 8 to 14 day hazards outlooks. This is what hazards we're expecting. These are also stale. I have seen the preliminary ones and they are more active, so I would look at those about 1 o'clock. Our seasonal precipitation and temperature outlooks, those will be coming out on Thursday officially. They do reflect a La Nina signature in them, so I would expect that to be somewhat similar on Thursday. And then looking at the drought outlook, both for the monthly and the seasonal, it looks like we are expecting drought to persist in a few areas in the south there, but mostly either removal or improvement for the Pacific Northwest. And then real quick summary, still in a La Nina watch. The potential this potential La Nina has been very slow to develop. Expect it to be weak. And again, want to remind you, the stronger the La Nina event, the more confident we are in typical impacts. So a little less confidence going into this weak event. The tropical atmosphere is really looking La Nina-like, so hopefully those sea surface temperatures are right around the corner, and all things indicate that's the case. And if you want to check out our outlooks, again, I apologize for the stale outlooks. My hands are tied. So please check those out later this afternoon, and then Thursday for the monthly and seasonal. And I'll wrap up there. Thank you.
Thanks so much, Andrea. And that is a great segue into our next presentation by Larry O'Neill. And Larry, I'll give you a heads up at 12 minutes.
Thank you. Well, good day, everyone. And my name is Larry O'Neill, and I am the Director of the Oregon Climate Service, and I'm on the faculty at Oregon State University, and I'm also the State Climatologist of Oregon. And today I'll be talking about the historical impacts of ENSO on Pacific Northwest reservoir storage. So I'm really glad that Andrea gave a little bit of perspective on how ENSO affects Pacific Northwest's hydroclimate variables and things. So I'll probably go through those fairly quickly. And this study was actually conducted for the upcoming Oregon climate assessment that will be coming out in January. And we did this analysis for Oregon, and I've extended it to include both Washington and Idaho as well for this presentation. And I'd like to acknowledge my co-authors, Rosie Una, who's a graduate student at Oregon State University, and Gabe Rivera, Nate Philman, David Rote, Nick Seiler, and Erica Fleischman. So obviously we talk about ENSO because it provides some predictability for our winter season in the Pacific Northwest. And the rule of thumb is that El Nino winters are warmer and drier, and La Nina winters are cooler and wetter. And so given ENSO's influence on precipitation and temperature, is there a consistent response of our reservoir water storage that we can tie to ENSO? So that's what the question I'll be answering today. And the way we categorize ENSO, as Andrea mentioned, was basically the ocean temperature along the equator in the Pacific, called the sea surface temperature. And the actual metric we used is an area average sea surface temperature, and it's called the Oceanic Niño Index, and it's in units of degrees Celsius, so it's temperature, and it basically just measures the departure of the equatorial sea surface temperatures from normal. And these anomalies in the sea surface temperature drive a response of the whole atmosphere over most of the globe, so it displaces the jet stream, and it gets wetter in some places and drier in others. And so this is why we look at ENSO for some level of predictability. For this talk, we're going to look at events since 1950 when the Oceanic Niño Index started. And during that time, there was a number of different events. And so we classify them by the strength of the temperature anomaly along the equator. And so this goes from strong La Nina, which is the coldest water. And the strength here is just basically the departure or the anomaly of the sea surface temperature. So when they're during a strong La Nina, that's when there's the coldest water along the equator. And then the warmest water along the equator occurs during El Niños. And the warmest possible occurs during what are called very strong El Nino events, of which there have been 3 since 1950. And we're going to talk a little bit about very strong El Nino in a minute here. But this is basically how we classify the phase strength. And so for the purposes of this discussion, we classified each of the water years between 1950 and 2023 and looked at several reservoir storage and precipitation as snowpack. So the way we looked at precipitation was to look at just the frequency of water years that were wetter than average for each of the El Nino or La Nina strengths. So for the strong La Nina, it's most of the time, there were 7 years in which there were strong La Ninas since 1950. And as you can see, the majority of the Pacific Northwest experienced more frequent wet water years during that time, especially in the Cascades and Western Oregon and Western Washington, where it's usually pretty wet already. And then in Northern Idaho and Western Montana, which is also fairly wet and mountainous in those areas. Exceptions are in Central and Eastern Washington, Oregon, and Southern Idaho as well. And so if we go down the different phase strengths, so moderate La Nina here, it's also more likely to be wetter than normal. Then when we get to weak La Nina, it's about even. So the greens here are more frequent wet and the browns are more frequent dry. So this one gets to about the whiter colors, which are equal chances of either way. There's neutral years, of which there have been 18, and it's slightly drier than normal everywhere. When you get to weak El Niños, it's slightly drier in the majority of places. Moderate El Niños, also fairly dry in the Cascades and Southern Idaho. Strong El Niños are very dry everywhere, so most of the region experiences much drier than normal years during that. And so looking at this pattern so far, you could think, oh, I can guess what the very strong El Nino will be. If it follows this pattern, it should be super dry. And it turns out actually that the very strong El Niños are mostly very wet. So some of our wettest years have occurred during the 3 very strong El Nino events that we've had since 1950. So that's the one takeaway, is that not all El Niños are the same in terms of precipitation. When we look at snowpack, this is just the water year traces of snow water equivalent going from October to September in each year. And I've just averaged them for the SNOTEL observations. So these are high elevation snow observations. And I just divided them up between El Nino and La Nina years and neutral years for each of the states. And in general, La Niñas have a larger snowpack compared to El Niños. And below here shows the percentages. Oregon usually tends to have the greatest response of La Niña and El Niño to the snowpack, but all three states, Idaho, Oregon, and Washington, generally have much better high elevation snowpack during La Niñas compared to El Niños. However, when you look at very strong El Niños, that pattern breaks down. So this just shows those same traces by the strength of the ENSO phase. So the blues are La Niñas, the reds are El Niños, and then the darkest red is the very strong El Niño. So most in all three states, the El Niños are much less snowpack than usual, except for the very strong El Niños, which has normal to above normal snowpack in all three states. Even though they tend to melt out a little earlier in Washington state. But the main takeaway here is that the very strong El Niños have wetter precipitation and more snowpack in the mountains. And we can also see this response of the stream flows to El Niño phase. And so this just shows that majority of the Huck 6 basins in Oregon, and basically shows this is the cumulative runoff versus time of year for the 12 Huck 6 basins in Oregon. And it basically shows that we get more stream flows and more runoff during La Nina years than El Nino, except for the very strong El Nino years in which we get some of the basins, especially in Southern Oregon, we get much greater runoff here. So we can already see that kind of predict here what our reservoirs might respond to this. And so this is a map of the major reservoirs in Oregon. And I picked these because they're the ones with the highest capacity in the state. And so there are 16 here. And I apologize for the busy graph, but I want to just kind of show, so there's some variation across the state. So in the reservoirs in Southern and Eastern Oregon, the greatest reservoir storage tends to occur during very strong El Nino years, followed closely behind by strong La Nina years. And then up in the Willamette Basin, which is in Northwest Oregon, there is not a consistent response of reservoir storage to ENSO, either in the rate of refill or the amount of drawdown here. So there is some dependence here. Now, if we go to Washington State, I picked 8 reservoirs here, and this one shows a little bit more consistent response. So most reservoirs in Washington experience their highest level during very strong El Nino years, followed closely by La Nina years, and then lastly is El Nino years here. So this is consistent with what we'd expect from just precipitation alone. And finally, here is Idaho here. So I also picked 16 reservoirs. It turns out Idaho is just filled with reservoirs. And here we also see the very same kind of dependence that we saw in Oregon, which is the southern reservoirs tend to have the greatest response to ENSO, such that the very strong El Nino years have much higher storage, followed by La Nina years, and then finally El Nino years have the least amount of storage. In the northern reservoirs in the Panhandle here, there also tends not to be as much of a consistent dependence of reservoir storage on ENSO phase here. And I made a table here just to show all these reservoirs I showed, what the difference in the peak storage is each year for La Niñas, ENSO neutral, and El Niños, excluding the very strong ones, and then the very strong ones here. And the take-home message is that the greatest storage compared to average is in the very strong El Nino years, followed by La Nina, and then the least amount of storage is in El Nino years, excluding the very strong ones here. So our key points, La Niñas are wetter in the Pacific Northwest than El Niños, and so this contributes to increased water storage in many reservoirs, excluding some in Northwest Oregon and Northern Idaho. And the exception to this rule is the strongest El Niños, which are the very strong El Niños. And those are the ones that we typically get the highest storage, peak storage during the water year. And I just want to emphasize that the significant variation in hydrological outcomes between the strong and very strong El Niños poses a significant challenge for trying to forecast water supply during the following spring and summer. And I just want to point out that during water year 2024, we had a borderline strong to very strong El Nino. And so that we had exceptional risk at that point, whether we were going to get a much drier than average outcome or a much wetter than average outcome. So if you have any questions, please email me here. Thank you.
Thank you, Larry. And hopefully we'll have time for a couple questions after Jessica's presentation. So now segueing into Jessica.
Can you hear me and do you see the presentation screen?
Yes, we do. And Jessica, I'll give you a heads up at 12 minutes.
All right, thank you so much. All right, so I'm going to be talking about how you can use the amount of snow we see on the ground right now, how much accumulates in the fall, to try to predict how much total we are going to get over the upcoming season. So to do this, the first thing is the baseline to be is climatology. Can we get the amount of snow at peak snowpack better than just guessing what it is on average? And to do that, there's two things we can take. We can do persistence, which is based on the fraction of peak SWE that's already on the ground by the date we're trying to make a forecast for. So on average, just from that, what can we predict for peak SWE based on seasonality? Or predictability, based on the amount of snow that's already on the ground, does it actually tell us, given the state of the system, that there's going to be more or less snow accumulating in the future? So let's start with our baseline climatology. So I'm going to be looking at two ways of looking at snow across the Western US. One is the snow tell, which earlier speakers have already presented. These just weigh the snow at a point, and these are for across the Western US and throughout British Columbia. I'm also going to be looking at some model runs led by Rae-Soon Kim across the Western US. And you can see that here in the Pacific Northwest, we have some of the most snow anywhere. So to do this, here are just an example for two different sites in the network. On the left is a site in the boreal forest of Alaska, and on the right is a maritime site in Washington. And the first thing is notice the different scale bars, right? The amount of snow that accumulates in Alaska is substantially less than the variability we get in Washington. In each of these, what I'm calling the baseline, which is climatology or what you want to beat, would be the black line. So this is just the median snow water equivalent at these sites. So we calculate what is the mean absolute difference, or MAD, in peak SWE over all the years compared to a prediction of the median peak SWE. So what kind of error would we expect if we just predicted right here where the red line is that, you know, the peak SWE will be the same it is on average? How much? It's another measure of interannual variability. If you look at this across the Western US, you can see that the variability increases as we move towards the coastline and towards the Southwest. So that the interior, some of these Montana, Idaho areas actually have less variation from one year to the next. So beyond climatology, what more can we learn by looking at the snow water equivalent on the 1st of December and the 1st of January? And here we are, we're sort of right exactly halfway in between that right now. So let's start with the snow on the ground on the 1st of December. So what we're going to start about is persistence, just asking how much of average annual snow accumulation is on the ground by the 1st of December. So to do that, we'll take the median snow water equivalent on that date divided by the median peak SWE for each date, and here we get a fraction. And what you can see is that, you know, really for most of the continental US, we're at about 20% or less of what we typically accumulate. But as if you move farther north up in Alaska and Canada, they've actually already have over 50% of the snow they're going to accumulate on the ground. You can also see that the primary driver of these December 1st patterns is driven by temperature, which makes sense. Colder sites have a greater fraction of their peak snow water equivalent earlier in the year, whereas warmer sites have been getting rain. The other thing to note is that the storm track is moving over this time from the north to the south. So the annual precipitation is higher earlier in the season in the northern latitudes. So what more can we learn by looking at the snow on January 1st? And to look at that, we can use the 1st of January SWE just with a really simple linear regression to predict peak SWE, where here we're looking at the mean absolute error or mean MAE regression error in our model. So in these cases, you can see here are the 2 snowtail sites I showed you before. And the red dashed line here is the linear regression. And so the scatter about that line is our regression error, MAE. And the scatter around climatology, which is the median or the blue line, is MAD. And you can see that anywhere where we have less error around our regression, we're doing better than guessing the climatology. So in Alaska, we have 20% less error. In Washington, we have 5% less error. And in the site in Wyoming, we have 14% less error. So if we map this across the entire Western US, where can we have in predictive skill? So you can see that west-wide, we have some skill, which I'm calling 5% or better, in Alaska, in the lower elevations along the coast, and in certain areas of the, I'm plotting the, so the red line here. So this is just interannual variability on the left, and then on the right, we are looking at the difference in the error between using the linear regression versus using just guessing climatology, the variation around climatology, where the red colors are improved skill just using a linear regression based on snow on the ground in the fall. So what you can see here is we have improvements up here in Alaska, we have improvements along the coast, and then right here in the Wind River area of the interior, we have some improvements. There's no difference for the area the first speaker showed in Drought right now. All right, so why? Why is it helpful? It turns out that for both Alaska and Wyoming, that the correlation of fall and winter precipitation help explain 2 of these. And so this could be due to sea surface gates, such as we just heard about La Niña and El Niño, or other large-scale atmospheric patterns that set this up. You can also see that for Washington, there is no correlation between the fall and the winter precipitation. So the interior areas, such as Granite Creek, which I showed, and Utes Peak, which I showed here, these are correlated because there is a correlation. So right here on the right, I'm showing the correlation coefficient of OND, or October, November, December precipitation with January, February, March precipitation. And you can see that throughout this area of the interior continental US and the upper Colorado, as well as interior Alaska, that fall and winter precipitation are correlated. However, you can see that along the coast, such as this is where the site Meadows Pass I was showing you, that despite there being an improvement in our predictive skill from the snow water equivalent, there is no correlation in precipitation. So what's going on here? So what's going on here is that these maritime locations, early season snow is actually critical to retain the water from subsequent mixed rain and snow events. So basically, if you have a cold or deep snowpack, the rain will freeze and be incorporated into the snowpack rather than running off. So this is an example for last year, which everyone in Washington called a very horrible year for skiing because we had so much ice on the snow. And so you can see here that this is Snoqualmie Pass. There was enough snow on the ground to get a crust at the end of December and keep that water in the snowpack. And again, in February, heavy rain on snow event kept the water in the snowpack. This is a simulation run by my graduate student, Clinton Alden, using the SUMA model. And what you're showing in addition to snowpack here is these lines are a very dense snow in the bright colors. And you can see that the snow gets really dense right where there are ice layers. All right, so we found in the coast, both coastal locations in Alaska and coastal locations in Washington and Oregon. They have skill, and if you plot these, where there's skill, so this is better skill is decreasing on this graph. when using a linear regression, and you can see that it's more skill at sites with warmer temperatures. Again, these are the sites that are getting rain on snow, and having early season snowpack keeps that rain and stores it for us for our peak snow water equivalent. So with this in mind, let's take a look at the current state of the snow-till site. So this is from this morning, where red is less than 50%, blue is greater than 150%, with green and blue being sort of close to normal. And what you can see is that for now, there's warm sites in the Olympics of Washington are looking like they have a good early season snowpack to keep things, keep the water around, and Southern Oregon is doing better. With the area, as the early speakers showed, right off I-90 by Seattle, this is where that Cedar River watershed is, they're doing worse, and so Snoqualmie Pass area will have less than usual snow accumulation right now, which doesn't bode well for the future right there. All right, so in summary, predicting peak snow from fall snow, January 1st has skill in northern and colder locations, mainly because a higher fraction of the season snow has fallen already. So it's mostly persistence. Places that are colder and further north have more snow on the ground by this time, and it will just stay there. Some upper Colorado locations have skill because October, November, December, and January, February, March precipitation are correlated. Warmer snow locations with more snow on the ground by the 1st of January will retain more mixed rain snow water for the rest of the season, increasing the total snowpack. So for this year in the Pacific Northwest, so far, it looks good for the Olympics and Southern Oregon, but not so great for sites along I-90. And everybody who's interested can check Snow-Tell again on January 1st to see how their favorite Snow-Tell sites are looking. Thank you very much. Are there any questions? This is my email, and if you want more details, this is the paper I was talking about. Thank you.
Thanks so much, Jessica. I am typing or pasting in everyone's contact information into the chat. There was one question about seasonal CPC forecasts, and Larry O'Neill mentioned that for the upcoming Oregon climate assessment, he and colleagues conducted a brief analysis of seasonal forecast models used in the CPC outlooks with respect to precipitation and temperature as a function of the ENSO phase. He said that temperature outlooks are somewhat skillful and precipitation was less skillful, but that they did not look at snowpack. We probably have time for one or two more questions. If anyone else has a question, would like to drop it in the question box. And if not, you'll all have 2 minutes. Let's see, can I get a copy? Is it possible to get a copy of the paper referenced in the presentation?
Yes, it's open access, publicly available online. I can send it to.
Great. Maybe that's something where you could send the link to Jason and he can make that available in the follow-up from the webinar.
Sure.
Great. Happy to do so.
Any other questions? Jessica, there's a question. I know you looked at the correlation between early and late season precipitation, but what about temperature?
I did, and I didn't. There is certain places, but I didn't find it beyond. I mean, I guess you could say the warmer sites had better predictability, and there was better predictability in warmer years. And yes, there is a correlation between temperature of October, November, December, and January, February, March.
Great, thank you. And I think we are at time. So again, please feel free to follow up with any of the individuals who presented or with Jason if you have questions. Links to the recordings will be made available, and thank you all so much for attending.